Okay, I think you're getting the idea here, but it's going to take a few days before you let that idea mature. But this is really kind of the last big concept you need in this course before we build all these concepts into really big concepts, okay? Which we really don't encounter until late November. But if you know what these things are in terms of this rectangular truncated parallelpiped, you get most of the course. You'll have something to use to understand most of the course. So anyhow, flux. I'm going to use the Greek letter phi, the letter just before phi, pho, and fum, okay? Or before pho and fum, it's phi, phi, pho, fum. It follows phi. Okay, well, anyhow. And actually, it's often pronounced phi, which really, then it becomes phi, phi, pho, fum, and that doesn't make any sense, so I don't know how anybody can pronounce this phi. Also, my fraternity was the phi size. If you pronounce this phi, it leads you to a very insulting pronunciation. So you might not even want to think about what that would be, but there we go. Okay, so your flux. And I never heard anybody actually use that, and everybody tried to insult us because we were insulting them, right? It's ridiculous. Okay, anyhow, your flux is, let me take one more. Your flux is your F perpendicular, okay? And I'm just going to define the magnitude of the flux right now because it gives you the idea. I could define it completely, very easily, in terms of a unit normal vector and stuff. And I'll probably mention it, but right now the concept is pretty. So it's simply the magnitude of the projection times the area of the surface. Okay? So what's this tell you? It tells you if you're shooting in this direction compared to if you were shooting in this direction. It tells you what proportion of your shots are going to hit compared to before, right? And you multiply that by the area, it could tell you how many shots you're going to hit, right? I mean, you could use it. The bigger the area, the more you're going to hit. So we take this magnitude of this projection and multiply it by the area. And it tells us how much stuff goes through here. How many of your bullets, how much of your fluid flowing, okay? Or how much of your gravitational or magnetic or electric field penetrates this surface, okay? Because all those things are modeled by vector functions. Functions of the vector function of x, y, and z, which is some vector for any point in space, okay? So that's kind of a big deal because this is really, I mean, we're really studying vector calculus, and right there is a big part of your picture of the things we're going to talk about. Okay? So now we're going to go back to chapter 10, have some assignments. I mean, I'll give you things here to work on and think about. I'll give you about a week to think through, okay? Because you want to get these ideas in your head, and you want to get these ideas in your head in relationship to this thing. Okay? Okay? You know, this has a normal vector. If it lives in a vector field where things are flowing this way or whatever, some percent of that flow will penetrate this surface. And of course, the bigger the surface is, the more stuff penetrates it, right? Also, if this is, you know, vertical, in an XYZ coordinate system, it's in the Z direction. Then the ratio of the surface area up here to the area of the base just depends on the normal vector and its angle with K. Right? A couple of fairly straightforward ideas. And we've also seen the idea that if you have a density function of X, Y, and Z, we can approximate the mass of this thing. Okay?